We begin with a new lecture of this course, Solar Photovoltaics. So what we have discussed in the last class was something on details of organic solar cells. So we discussed the details of organic solar cells. We looked at why is there a need to increase the thickness of organic solar cells so that we can improve light absorption. This is countered by the fact that exciton have low diffusion length in the organic semiconductors, but we can make innovative designs such as bulk heterojunction, which gives rise to bulk heterojunction, which is a nanoscale mixture of by mixing P and N type materials at nanoscale, so that you bring the interface closer to exciton than to bring the exciton closer to the interface. So interface, wherever exciton is formed, it finds a interface in the vicinity, and hence it is able to, and then interface provides an electric field to break it up in the carriers. Another requirement is that the two phases must make a continuous network, interpenetrating network, so that carriers are always able to diffuse to respective electrodes. If they are not able to move to different electrodes, then they will again be lost. As a result, it is important that the network of two phases is continuous at even at nanoscale it must be continuous. So ideally you would like to have a structure like this. So let us say you have these two electrodes, this is the ideal structure you would like to have, interpenetrating network. So this is one phase, and this is another phase. You can say this green one is the another phase. So you have one phase making a good contact with cathode and another phase making good contact with the anode. This is the ideal picture. It will not always work like this, but this is what is the desirable aspect. And every side, on the two sides, we also have carrier selective layers. So we call them as HTL/ETL, electron transport layer or hole transport layer. So this would be again HTL or ETL, electron. So H hole, E electron, TL mean transport layer. Some people also call them as hole blocking layers or electron blocking layers because they block the other carriers. So and then we will have electrodes on the two sides. These would be the electrodes. So this is a typical structure that you will device structure that you will see. Generally the way these devices are made is very simple. So manufacturing is very straightforward, but it is done in controlled environment. Okay. So first what you do is that you clean the substrates, and substrates are generally ITO coated glass, and this ITO has a sheet resistance of 5 to 10 ohms per square preferable. Okay. So lower sheet resistance is preferable. Clean the substrate, then you pattern the substrate, so that the junctions are made at designated places. So you pattern the substrate for a device, for a given device structure, for a given device. Then we deposit hole transporting layer from the solution of, and this is done by spin coating. Okay. then and deposit spin coating followed by annealing or heat treatment at a given temperature. Okay. So, what is important at this stage is the spin speed, the spin time, the amount of material that you put, the time at which you anneal, the temperature at which you anneal, time for which you anneal and temperature at which you anneal. This will determine the thickness and microstructure of that. So, this is generally of the order of 10 to 40 nanometers. Okay. That is the idea, depending upon the type of material. Then you deposit the active layer blend, and blend is basically a solution of P and N type materials such as P3HT, polyethylethiophene, and C60, that is fullerene. We call it as PCBM, PC60BM. Again, you spin coat it at a given spin speed for a given time, followed by heat treatment. This is generally done in controlled ambient such as nitrogen ambient. Okay. And then anneal it at certain temperature for certain time to get a thickness of the order of about 100 nanometer. So, again same method, spin coating followed by annealing. Then we deposit what we call as deposition of electron / hole transporting layer. So, in this case it could be hole / electron transporting layer. So, if it is hole, then you deposit electron, if it is electron, then you deposit the hole, right, and then we deposit what we call as electrode. This layer is often deposited using evaporation, because once you deposit active layer, you do not want to damage it using solvents. So, because solvent can dissolve the active layer, as a result we generally deposit it using a process called as evaporation, and then we evaporate electrode through the shadow mask. So, again this layer is about 10 to 40 nanometer thin, it could be 5 also in certain cases, and electrode is about 100 nanometer thin. So, you can see the whole device thickness starting from whole transport layer is of the order of 200 or 250 nanometers. So, very total device thickness is like if you also include ITO, it is about 300 nanometer except glass. So, it is a basically nanostructured device. So, as a result the way you manufacture is very important, that is why you manufacture these in clean environment. If you have a dust particle, if you have any other second phase present here whose size is more than the size of the thickness, then you kill the device. So, it is very important that manufacturing is done in clean environment with controlled humidity, because these polymers are very susceptible to humidity. So, there are different heterostructures that are present in the literature. So, the one which are based on for example P3HT PCBM, PC60BM, they give you efficiency of the order of 4%. The current that we obtain is of the order of JSC is of the order of 10 milliamps per centimeter square. The VOC is of the order of 0.6667 milliamps per centimeter volts, and the fill factor is of the order of 65 to 70% in these devices, 4 to you can say 5%, the best devices. Okay. The ones which are based on another polymer PCDT-BT, and in this case we use PC70BM as a, so this is donor, this is acceptor. These heterojunctions give efficiencies of the order of about 6 to 7% and VOC of the order of nearly 0.9 volt and JSC of the order of 10 to 11 milliamps per centimeter square. We have another material which is recent material PTB7, PTB7 based device, and they are again with PC70BM. This is a donor, this is a acceptor. Here also P3HT is a donor and this is a acceptor. These devices give you efficiencies of the order of nearly they give you 10 to 11%. VOC is of the order of 0.8 volt, 0.81 volt roughly. JSC is of the order of 17 to 19 milliamps per centimeter square. Fill factor is about 70 to 75%. The organic tandem cells where you combine various polymers. So, organic tandem cells, they give you efficiencies of the order of about, so right now we have about 17% obtained. This is in 2018 reported, and they use again the same multi-junction concept, that by stacking materials of different band gaps. Okay. The problems, there are however certain problems with organic solar cells, issues with they degrade in ambient conditions. So, efficiency for example degrades from about 4% to nearly 0 in few days for a P3HT PCBM. And sometimes so these degrade very strongly. So, nearly more than 50% reduction in a few days, in fact for certain materials in a few hours under ambient conditions. So, what is important is, and why this happens is that this happens because of reactivity of constituents with oxygen, with moisture, and also photo-induced degradation. There are multiple degradation mechanisms that are present in the literature. There are a lot of reviews available. So, degradation could be chemical, it could be physical, and it could be photo-induced. All these three types of degradations are possible. So, the constituents such as active layer, hole transporting layer as well electron transporting layer, all the electrodes may chemically degrade upon reaction with oxygen and moisture. They may physically damage, their morphology will change, and the light accelerates the process in many cases. So, these materials are prone to degradation, and that is one of the reasons why they have not made it successful commercially. Why they are not successful commercially, because of this degradation issues. Of course, efficiencies are lower, efficiencies are low at a module level, efficiencies are low at module level, and poor degradation characteristics. So, these two problems have led to unsuccessful commercialization of these technology. However, a lot of efforts are on to improve the degradation characteristics by developing better materials, by making better encapsulants which can prevent the diffusion of moisture and oxygen into the devices. So, work is still on to improve these devices. So, this is still a technology which is pretty much extensively being researched, and it is quite promising for future. So, next we will move on to another promising technology, which is third generation technology, is dye sensitized solar cells. So, these dye sensitized solar cells are different from normal solar cells in the sense that they are also electrochemical solar cells, and they use a different principles of electricity generation as compared to organic or inorganic other solar cells. So, what you have in these devices is something like this. So, we have a glass substrate on which we have a transparent conducting oxide electrode. So, this is a TCO, which is some conducting oxide, and then on top we have what we call as a electrolyte. So, here we have a electrolyte, which is normally a iodine conducting electrolyte. So, it has I minus, I3 minus ions, and then we have what we call as a TiO2 nanoparticles with a light sensitive dye. So, TiO2 with dye, which makes a sort of nice interface with the, so interfacial area is very important between the dye. So, this is, you can say, TiO2 with dye, and this dye is photosensitive. And then again we have on top a layer of TCO. So, this is TCO, transparent conducting oxide, and then again on top we have a glass layer. And when you connect these TCOs, we have load, and we get the electricity out of it when we shine light to it. And this layer is about, in this case, nearly 10 micron thick, the main TiO2 layer. This was co-invented by Brian O'Regan and Brian O'Regan and Michael Gratzel in 1988. So, in that sense it is much older than organic solar cells, and but it is very promising because of simple nature. It uses very simple materials, it uses glass substrate, it uses some sort of transparent conducting oxide, it uses electrolyte which has iodine as the principal species, and then it is in contact with the TiO2 solid network, which is impregnated with the dye. So, the way this solar cell works is like this. So, what happens is that when the first step is the dye, so you can say the dye absorbs the light, that is step number 1, and then the dye, let us say, is designated by S. When it captures a photon, it gets excited. So, this is excitation of the dye. This is number 2. Then this excited dye, which is in contact with the TiO2, leads to electron generation. So, this is, you can say, so this sensitizer becomes photo excited, photosensitizer becomes oxidized. So, from excited state, this dye becomes oxidized, between the electrons is created. This electron then moves through the TiO2. So, this is called as injection process, you can say this is injection. So, it has injected a electron. This is number 3. This electron then, which is going through TiO2, goes to the counter electrode, which is CE is the counter electrode. So, TiO2 again goes back to its state. the electron goes to the counter electrode, and then this gives rise to what we call as electrical energy because it is connected to a load. So, this step is called as energy creation process. This is number 4. So, this electron then goes, so what happens is that, so you have the light has fallen here, okay, sorry, the light has fallen all over the cell, the die has gotten excited, the electron goes through TiO2, it goes through TiO2 to TCO, comes through the electrical circuit. So, electron is going like this, comes back to this. Once it comes back through the reverse circuit, then this, so what happens is that this now the die gets regenerated, because remember die was in S plus state, so it has to get regenerated. So, this die gets regenerated by, so this makes, so there are two processes which happen. So, once the electron reaches, first is a recapture of electron, they happen simultaneously, recapture of electron. So, you can say this is 5 and 6, and then we have regeneration of die. So, this regeneration of die happens, this S plus reacts with 3 by 2 I minus to give rise to S. So, it comes to normal state I3 minus, this is regeneration, okay. And then this I3 minus half I2 3 minus, this reacts with the electron that has reached back from the circuit from the other side, and this gives rise to 3 by 2 I minus plus what we have is then counter electrode, right, electron, it's come from the, so this is electron recapture, basically we do not have to write this. So, this is electron recapture essentially. So, this is what is the overall principle of operation. So, what has happened is, let me now, so first is light absorption by the die, then we have excitation which results in the electron production. This electron travels through the TiO2 because TiO2 is a n-type conducting material. So, TiO2 is a n-type conduction, right. So, it happens through n-type conduction through TiO2. TiO2 is an n-type conducting material, it is a nanostructured TiO2, nanostructured is needed because it has maximum interfacial area with the die. So, it is a nanostructured TiO2, we can say this is nanostructured. The electron then goes through TiO2 to the counter electrode, and then it travels from the circuit to the other electrode. On the other electrode, then this electron gets captured, this leads to formation of this 3 by 2 I minus. This 3 by 2 I minus is basically, it reacts with the iodine I3 I think it is I3 minus 1 minus, yeah. So, it deals with this I3 minus ion, gives rise to 3 by 2 I minus. This 3 by 2 I minus reacts with the excited die molecules to convert that back into the normal unexcited state. So, in this case what we have is regeneration of the die. So, basically the electron which travels back from the circuit, it reacts with the iodine ions to ensure, and those iodine ions are then converted from one state to another, which then react with the excited state of die ions, so that you have complete process. So, again we have first is the light absorption, second is the excitation to result in electron production, third is the diffusion of electrons to the TCO via TiO2 nanoparticles. These electrons then reach the counter electrode, and then this counter, because you have a circuit which is connected. So, from the counter electrode they travel through the circuit, and then we have a redox reaction. That redox reaction means that you have this, you have to convert the excited die molecules to the normal die molecules, which happens via oxidation of iodine ions, and then so oxygen iodine ions, they convert, they absorb the electron to go. So, first they reduce, and then the bigger iodine ion reacts with the excited die molecule to give you a final state. So, we have redox reaction and then diffusion to the counter electrode, where oxidized redox mediator is reduced to I minus ions. Okay. So, we have these 5, 6, you can say 5 and 6. So, this is 5 and this is 6. So, these 6 steps which complete the process of an electricity generation in dye sensitized solar cells. So, what are the key components in this? So, it is a very simple concept. The key components in this solar cell are the first one is you must have a nanostructured TiO2, which is also called as a photoelectrode, in contact with dye. So, you want to maximize the nanostructure TiO2 is there. People also use zinc oxide. So, this is optimization of this TiO2 is extremely important through careful processing. Then we have photosensitizer. This photosensitizer is normally, for example, it could be polypyridyl compounds of ruthenium or osmium. So, it is one of these two materials. So, basically the dyes are basically ruthenium based. Okay. So, ruthenium based, in most cases they are ruthenium based dyes. Ruthenium based dyes have good photosensitivity as compared to other dyes. You can also use natural dyes, such as, if you just want to demonstrate a solar cell in the lab to children, let us say school children, then we can use henna, for example. Henna is a dye that we know, mehendi as we call it, and then we have natural anthocyanins. Rosella is another dye which is a natural dye, and then we have black rice, that is also a natural. So, these dyes can also be used for demonstration of solar cells. As far as electrolyte is concerned, electrolyte is generally, its electrolyte contains I minus and I3 minus ions. So, basically redox ions which are used to regenerate the oxidized dye molecules, as we saw earlier how they are regenerated, and to complete the electrical circuit by mediating the electrons between the nanostructured electrode and the counter electrode. Okay. So, these are this is the constituent of electrolyte. Generally we have things like sodium iodide, lithium iodide, etc. They are dissolved in non-protonic solvents, and these solvents are acetonitrile, it could be propylene carbonate, and so on and so forth. And conductivity of ion, so in this case the ions have to diffuse in and out, right. So, as a result the conductivity of ions is very important. So, ionic conductivity of electrolyte is an important concern. Should be good, and this is also affected by the viscosity. So, it is the interplay between the viscosity and the conductivity. So, this is so finally we will just look at something related to efficiency. So, efficiency in these depends upon the excited state and the ground state of the sensitizer. because it depends upon what kind of band gaps it does absorb. So, energy levels within the sensitizer, photosensitizer, that is. Then we also have to have Fermi level of TiO2 appropriately placed, so that electrons are able to conduct themselves. And then we also need to have appropriate redox potential of I minus, I3 minus in the electrolyte. Okay. These are the factors which affect the efficiency of these solar cells. So, maximum efficiencies that we have got is about 14% right now. So, these are the problem is presence of the dye is liquid, which can be controlled to some certain extent using solid dye. So, we will stop here. What we have discussed is dye sensitized solar cell, organic solar cells in this lecture. We will take one more lecture to finish off with the perovskite solar cells. Thank you.